turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists.
Hello and welcome to The Naked Scientist, the show that brings you the latest in science, technology and medicine. I'm Will Tingle, and this week I'm exploring the phenomena of black holes. Firstly, what are they? Secondly, where can I find one? And thirdly, what would happen were I to fall in and maybe even get thrown back out?
The Naked Scientists podcast is powered by ukfast.co.uk.
Black holes are one of the most extreme things in the universe. Their gravitational pull is so strong they can bend light and even time. So were I to find one and fall into it, what would happen to me? To help me find out more about what I should expect, I went to visit Chris Reynolds, who is a professor of astronomy at the University of Cambridge. He gave me the rundown on how these mysterious regions of space-time work.
the best way to think about what a black hole is by think about how it might form. Gravity is an incredibly powerful force. And the key thing in nature is that gravity can actually, in some circumstances, overwhelm all other forces. So if you have an object that has a lot of mass and the mass is collected into one place, then you can have so much mass collected into one place, the gravitational pull of that mass, the gravitational force that's sort of crushing that mass down, can actually overwhelm all other physical forces. And the object just starts falling in on itself. And it falls in on itself and keeps on falling in on itself. Nothing can resist that. And theoretically, it falls all the way into a point. Now, in doing that, something really interesting happens in that it actually seals itself off from the rest of the universe. The speed of light is a fundamental speed limit on anything. It's a speed limit on, of course, how fast light can go, but it's also a speed limit on how fast information can be communicated from one place to another. And as the object starts to fall in on itself, the escape velocity of that object, in other words, the velocity that you have to leave with in order to actually escape the object, goes up and up and up. And at some point, the object is now so dense that you would need to be thrown off it at the speed of light or faster to actually leave. And there's a point of no return that surrounds it called the event horizon. And when you think of a black hole and you think of that black sphere, that's what you're looking at. You're looking at that event horizon, the point at which nothing can actually get out.
So are all black holes the same size?
That's a good question. We know of at least two classes of black holes. There's what I would call small ones, which are from the collapse of stars. The core of the star undergoes a collapse, and boom, you have a black hole. In doing that, the energy released in forming that black hole can blow the rest of the star up in a supernova. What you're left with is a black hole that is maybe about 10 times the mass of the sun. Now, the other class of black holes we know about are the supermassive black holes. These are black holes that are anywhere between 1 million to sometimes up to 10 billion times the mass of the sun, and they sit in the center of galaxies.
Are all black holes active? Is there such thing as a dormant black hole?
It's probably just a matter of degree. Any black hole, there'll be some trickle of gas or dust or whatever's around it into the black hole. As that gas is falling in, it will be releasing some of its energy, it will be emitting light, and so there'll be a little bit of what we would call activity from that black hole as that gas is falling into the black hole. However, there are certainly a subset of black holes, there's a small fraction, maybe 1 to 10% of supermassive black holes, for which there's a lot of gas falling into them, there's a lot of matter falling into them, and they really light up. You can see them across vast distances. So those are what we normally think of as the active black holes. The terminology we use is active galactic nuclei.
Perhaps the most mysterious aspect of the black hole is the middle. Do we know what's going on in the middle of a black hole? Can it even be called the middle?
Well, yes, that is the profound mystery of what's happening in the very center of the black hole. This is known as the space-time singularity, is the technical term for it. It's a very hard region to understand, firstly because theoretically there are such great uncertainties about it, but also we can't see it. So we can't get data on it, which makes it, of course, very hard to understand. In fact, some people would even say it's not science because we can't get data on it. The nature of the space-time singularity is actually very closely wrapped up with some of the profound questions about black holes that Stephen Hawking asked. Stephen Hawking was asking questions about how black holes and information sort of played with each other. There was this profound mystery that, according to our standard theory of gravity, if you were to take a black hole and then throw, a book or hard disk into the black hole, the information on that book or the hard disk would just be completely lost. You just destroy that information. However, quantum mechanics, the other theory that underlies modern physics, tells us that's impossible. You can't destroy information. So, how do those two pillars of physics play with each other? That was a big concern of Hawking and many other theoretical physicists in the past few decades. And it gets very closely wrapped up with issues of that singularity.
Many of us have seen films like Interstellar, which make great plays on how black holes affect time. Presumably it's all to do with their immense gravitational pull. But in your own words, how does a black hole mess with the concepts that we have of time?
Yes, so black holes do mess with time in a very interesting way. Fundamentally, as you get closer to a black hole, time starts to slow down. What does that mean? What that means is if you're a long way from a black hole and you're watching a friend going into a black hole or getting close to a black hole, and you can sort of see the clock that they carry with them, you start to see their clock running more slowly, and you start to see them aging more slowly. They, of course, don't think anything's going wrong. They see time passing perfectly normally for them. If they're looking out at you, though, they would see your clock running fast, and they'd see you aging fast. So that's what the theory tells us. And indeed, one way to think about the event horizon, this is that point of no return, is that all these effects get stronger and stronger and stronger until you get to the event horizon. And then if you're looking from the outside, that's the point where time basically seems to stop. If your friend is right at the event horizon, you see them basically frozen in time.
That was Chris Reynolds at the University of Cambridge. Now that I know what I'm dealing with, I need to know where to find a black hole. The first instance of a recorded black hole was in 1971, and we've discovered dozens since then. But how do you spot a black hole in a mostly black universe? Well, perhaps I should ask someone who's done exactly that. Dr. James Nightingale is a physicist at the University of Durham and recently found a supermassive black hole 33 billion times the mass of our sun. He told me about the different ways you can go black hole spotting.
There's many different ways that we discover black holes. I'll specifically focus on the discovery of some of the biggest black holes, which are called these supermassive black holes. And these were first discovered from sort of the 1970s onwards, when we started looking at the stars in the centers of galaxies nearby the Milky Way. So if a galaxy is very close to the Milky Way, we can actually resolve all of its individual stars as little point sources. And we can actually measure the velocities of those stars, so we can determine how fast those stars are either moving away from us on Earth or coming towards us. And we can monitor those velocities over the course of years or even decades. And what we basically found in the 1970s was that towards the centers of these nearby galaxies, the velocities of the stars were showing sudden increases. As a star moved through or towards the center of a galaxy, it began to really, really speed up. And the only real explanation one could have for this is that something must be causing the stars to speed up, some sort of intense gravitational field exerting Newton's second law, bringing the stars further towards them, which was ultimately decided that therefore it must be giant black holes, some millions of times the mass of the sun, that was causing the stars to speed up in this way.
So it's never really about seeing them directly, it's about being able to infer them from movements of things we can see.
Yeah, exactly. Obviously, you can never see a black hole directly, and I don't think all of the ways that we discover black holes, all of the ways that astronomers assert their existence and measure their masses are reliant on, typically reliant on their intense gravitational fields having knock-on effects or consequences, which are what we observe. So in this case, it's the gravitational field of the black hole changing the orbits of the stars around it. But basically all of the ways that we infer the presence of black holes are somehow related to the knock-on effect of the black hole's intense gravitational field.
as you say, there's a bit of a resolution problem if we're trying to find something perhaps more distant than inside our Milky Way. What are we doing now to look for more distant black holes?
In order to infer the presence of these black holes, though, we have to look for a different phenomena. And so in the centers of galaxies, as we've said, there are these supermassive black holes, and they sometimes are feeding on the material in their galaxy. They're in what's called an active state. So these supermassive black holes at the center of the galaxies, they might be eating the stars in the galaxy surrounding them. They might be eating its gas. They might be eating its dust. They might even be eating other black holes within that galaxy. And the key thing is, because they're bringing all of the galaxy's material to their center, because their gravitational field is bringing in all of this stuff, basically, this material at the center of the galaxy begins to undergo intense levels of friction, intense levels of heating, and therefore begins to emit extremely bright amounts of energy across the entire electromagnetic spectrum at the center of the galaxy. So in a very small subset of galaxies, we observe this extremely bright emission at their center, which is, of course, indicative of the black hole being there.
So it's almost paradoxical then that in looking for black holes, we look for the lightest parts that we can see.
I think you always have to be careful here, because although black holes are obviously famously invisible, famously don't emit light, they are also the brightest things in the universe, but it's specifically the stuff that's outside the event horizon, but still very, very close to the black hole that does that. So it's not actually a paradox. It's simply that the stuff we're seeing is slightly beyond the event horizon of the actual supermassive black hole at the center.
And you pretty recently spotted your own supermassive black hole. How did you go about spotting yours?
The paper myself and my team put out used a technique called gravitational lensing, and was actually the first time that the mass of a black hole, or a black hole in general, has been discovered using this technique. And so gravitational lensing is a phenomena where basically, as the light of a distant galaxy travels through the universe, you imagine a light ray, a photon just traveling through the universe, the path of that light ray will be slightly distorted and deflected by any of the mass it encounters along the way. The gravitational fields of, let's say, other galaxies will cause that light ray to come slightly towards those galaxies. Using the Hubble Space Telescope, we found this wonderful gravitational lens where we observed it had 4 distinct light rays that had all been distorted and deflected and warped by another galaxy that was perfectly in front of it. But what was particularly special about this gravitational lens is that one of these light rays that has traveled through the universe, one of these gravitationally lensed collections of photons, traveled right next to the center of another galaxy that was responsible for the gravitational lensing. And it traveled so close to the center of that galaxy that not only was it deflected by the stars within that galaxy, but the black hole at the center of that galaxy also caused an additional bending of light, an additional contribution to this gravitational lensing effect. And so we basically observed with Hubble this image of a galaxy that was so distorted, so deflected, so bent by the material in the universe that the only way that we could explain it was the presence of an extremely large 33 billion solar mass, that's 33 billion times the mass of the sun, black hole at the center of this galaxy that the light ray just happened to pass by.
So purely hypothetically, of course, if there was someone out there hoping to go to a black hole for research purposes, would you recommend them heading towards the center of a galaxy for the brightest bit? Would that be your best bet?
I mean, yeah, I think so. I think that the smaller a black hole, the more rapidly changing its gravitational field. So if you head into a black hole that's only a couple 10 times the mass of our sun, you will be ripped apart, or spaghettified is a common term used, almost instantly. As black holes grow larger, the gravitational field actually changes at a much slower rate, or a much more gradual rate, which means you could feasibly fall into a black hole as large as the one I've discovered and not be ripped apart by the intense gravitational forces. Now, don't get me wrong, you'll probably have a lot of other very nasty consequences to deal with, but at least the gravity itself would probably just about be bearable for a human. So I would definitely recommend, if you're set on traveling to the center of a black hole, definitely pick one of the largest possible.
That was James Nightingale, and if you want to know more about his research, it's available on the University of Durham's website.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to The Naked Scientists with me, Will Tingle, and this week we're looking at the subject of black holes. In a moment, could there ever be such a thing as a white hole? But before that, it's time to jump into a black hole. I've been sufficiently prepared for my voyage into the unknown, and I'm now coming to you from just outside of a supermassive black hole. I went with Sagittarius A, the supermassive black hole at the centre of the Milky Way. It has a mass of 4 million suns, and I'll explain why I picked this one later. But for now, let's do this. The effect starts slow. A black hole this big has probably been gravitationally influencing me even slightly for millions of miles at this point, although up until now I will have been able to escape it. The chances of escape are, however, diminishing the closer I get to the orbit of the black hole. How close before it's a noticeable pull, of course, depends on the size of the black hole, and I recall the words of wisdom from the Royal Observatory at Greenwich's Ed Bloomer.
I tried to do the sort of back of the envelope calculation, and I was working with a black hole that had twice the mass of the sun, because that's about the lower limit of black holes that we kind of traditionally make with supernovae. Once you're about 5.5 million kilometers away, then the pull on your body just from that black hole would be about the same that you would experience right now here on Earth. So you'd feel like you sort of weighed one standard Earth gravity just because of that black hole.
This black hole, however, is many, many times the size of that one though, so the feeling of Earth-like gravity started a lot further away. The pull is increasing, and it feels like I'm beginning to accelerate.
It's the nature of the gravity itself. The closer you are to the gravitating body, the stronger the pull, and that accelerates somebody.
More time passes, although not nearly as much time as will be passing on Earth. With such a massive time dilation, 1 minute here is about 700 years on our planet. So sorry if this goes out a bit late. Physics is starting to get really funky now, because light is orbiting the black hole in a circle. If I look around, I might be able to see the back of me. The brightest object in the galaxy could now be my bald spot. But I can take solace in the fact that anyone observing my fall is seeing some pretty weird stuff too.
I don't want to go near this black hole, so let's say I watch you fall into it. From my point of view, I think you are slowing down, and the time itself is passing at a different rate, as in fact it is. But also, gravitational redshift is happening. The immense gravity of the black hole means that these electromagnetic radiation waves, whether that's radio or whether you're shining a torch at me or whatever, they're being stretched to larger and larger wave strengths. So actually, in fact, you're not only just changing color, eventually your radio signals are going to be stretched out to the point where I can't actually receive anything from you or indeed see you anymore. Eventually you would be lost to vision as well.
Good job I'm recording this on a handheld device then. Eventually, I hit the point of no return. If I were made of light, this would be the event horizon or the Schwarzschild radius, but given that I'm not and my bathroom scales assure me that, it's a bit further out.
There's a point where you cannot maintain a stable orbit, and it depends on the situation, but let's say best case scenario, about 4.5 times what we call the Schwarzschild radius, which people sort of tend to think as the last stopping point, but actually about 4.5 times further out than that. That's the point at which you are not going to be able to prevent yourself from falling into that black hole.
Passing over this point, and then the event horizon, the forces of gravity coming from the singularity at the centre are conspiring to pull me apart. The difference in gravitational pull and the distance between my head and feet is so large that I would be pulled apart. Think of the centre of a black hole as a tube, and the smaller the black hole, the smaller the tube I would be squeezed through. It's called spaghettification. It sounds like a grim way to go, and in smaller black holes, that would be the case. But this is why I picked a supermassive black hole.
When you have much more mass in the black hole, the size of the black hole scales up with that mass. And what that means is when you have truly, truly massive black holes, the gradient is a little bit more gentle for you. And in theory, depending on the mass of the black hole, if you've got truly massive black holes, you could have a gradient that's gentle enough that spaghettification won't be the end of you, which means that you could actually get pretty close to the event horizon. But it would only be, I think, about 25 times Earth's gravity.
25 times the gravity of Earth is barely anything. So assuming I've survived being squeezed, I am curious as to how I might meet my end.
It depends what else the black hole is doing, because in fact, as other objects fall into it, they accelerate and they produce X-rays and even gamma rays. So in fact, actually, if other dust clouds and things like that, little particles are falling into the black hole, possibly long before you have a problem with, the actual mechanics on your body, you're actually being blasted by gamma rays from the black hole. So incoming radiation might actually be the thing that kills you, I'm afraid.
So I may well go out as a well-done steak rather than a piece of spaghetti. Assuming neither of those happen, I enter the circle of the black hole as it consumes me. The rest of the universe now only looks like a circle of distant light that is rapidly fading. I mentioned physics was funky earlier, but now it kicks into overdrive. Due to the nature of the singularity's gravity, every direction is now inward. Any attempt to move away from the black hole would actually bring me closer towards the center as we enter the singularity. What happens next is contentious and depends if you think a black hole completely destroys the matter that it takes in or just compresses it down to near infinity. But either way, I am stripped of my being and the atoms that made up my existence are crushed and join the infinitely dense point. I become part of the black hole. That wasn't so bad. But if I've done my job right here, I'm sure many of you have noticed something that doesn't stack up. How, if not even light can escape a black hole, are you hearing this recording? Surely it was crushed along with the rest of me. Well, the answer is quite simple. I was spewed out of a white hole. Sorry, did I say simple? I meant hypothetical quantum physics. White holes are, for now, the theory that if a body can exist from which nothing can escape, that's black holes, then there could be something into which nothing can enter. And if you subscribe to the theory that black holes do not destroy information, there might be a way of it coming back out. My head hurts too, but our best chance of understanding this might lie with theoretical physicist and author of the upcoming book White Holes, Carlo Rovelli.
And what is a white hole? It's a black hole as if it would look like if you could film it and show the film backward. So it's sort of a black hole coming back. So the idea here is that black hole, white hole could be like a ball falling to the ground and bouncing up. So everything that falls in bounces and comes out through the white hole.
How would a white hole form then? Is it just a black hole that's almost collapsed in on itself and then, for lack of a better word, exploded back outwards again?
Yes, exactly. So one way of visualizing a black hole, what's going on inside, is that there is a horizon, a surface, the thing of the black hole we see from the outside, but inside there's a long tube that becomes longer and longer and longer and narrower until the point in which it's so narrow that quantum effects make it bounce back. And so this long tube starts becoming thicker again and shorter, comes back. So the formation of this tube bounces into a coming back of the tube itself, and that's a white hole. From the outside, first we see the horizon where everything comes fall in, and then we see the white hole, which is the same horizon, the same position in the sky, the same star, if you want. But now, instead of an horizon where everything can only go in, it's an horizon from which everything can only go out. So whatever is inside now can bounce out, and that's a white hole.
And what would cause the black hole to sort of flip in a quantum sense, to start throwing stuff back out?
One of the things that quantum mechanics tell us about the world is that many things that we think are continuous are actually granular. So light is made by photons. It's not a continuous wave, it's just the little grains, which are the photons. And if you apply quantum mechanics to space itself, it tells us that space is granular. So a black hole cannot squeeze things down to infinity. There is no infinity small. At some point, you get to the minimum size. And once you get to the minimum size, the fall is blocked, so to say, and you cannot fall it more, and it has to stop. And when things stop falling, typically they bounce. If you want, black holes is a solution of Einstein equations, which we understand very well, except how they end. And white holes is a solution of Einstein equations that we understand very well, except how it starts. So it's extremely plausible to imagine that when a black hole ends, that's exactly the quantum transition to a white hole being born.
What kind of matter would it spit out? Would it be recognizable? Would it just be pure energy? What kind of things would we be looking at?
We would expect that what spits out is just ordinary matter radiation, more likely, like electromagnetic radiation, very much unrecognizable with respect with what fell in, because things are going to be squashed horrendously by falling into the black hole. Calculations suggest that what could come out is very low energy radiation. So like light of very, very low energy, very low frequency, which is one of the signals. There are many of these things. It could be another of the signals that one might search to identify the existence of these objects.
We have to stress at this point that we haven't actually observed a white hole yet. This is all theoretical for now, but is that simply because we don't really know what to look for yet?
No, it's more than that. We don't know if this scenario is correct or not. We don't know if white hole exists in the universe or not. We have to remember that for almost a century, black holes were predicted by general relativity, and many people didn't believe they existed. It was an open question. When I was a student, I studied black holes, and my teacher in my textbook said, well, it's implausible that these things exist in the universe. So we're in the same situation now with white holes. They're predicted by general relativity, but we don't know whether they exist in the universe or not. To me, it seems very plausible that they do, and it seems very plausible that the end of a black hole is the birth of the white hole. But until we're actually seeing them or seeing an effect of them or consequence of them, we have to consider white hole hypothetical ideas.
There's lots of theories going on about white holes and black holes and their relationship. And one of them is that white holes don't exist in this universe, they exist in another universe, and there's some form of door that exists between black holes and white holes. Do you subscribe to that theory, or do you think there's something else going on?
I think there is something else going on. I think that when the black hole die, three things can happen. One is that everything disappears magically, but that seems implausible to me. The second possibility is that it ends up in another universe somehow, or it creates another universe. This is a beautiful, enchanting idea, but it doesn't seem plausible to me. I mean, creating another universe might not be so simple as collapsing a star. And the third possibility, we just talked about, namely that whatever fell in can come out because the black hole becomes a white hole. So the entire process, formation of a black hole, evaporation, and then formation of white hole and coming out, is just like a ball that falls to the ground and then bounces up. One of the fascinating aspects of this story for me is that in general relativity, time goes at very different speed, as we know. Time goes faster in the mountain than near the sea on Earth, but that's teeny difference. Now, if you work out the speed of time inside the black hole and the white hole is enormously slower than outside. So the process seen from the outside of a star collapsing and then becoming a white hole and coming out may last billions of years. But if you fall inside, it takes just a few seconds or minutes for you to get to the center and come out as a white hole. So black hole to white hole might be just like a shortcut to the very distant future. If you survived and wouldn't be squashed by the enormous forces inside the black hole, you could just jump to the black hole and come out from a white hole, but very, very far in the future, millions or even billions of years in the future.
That was the author of White Holes, Carlo Rovelli. So we may have only scratched the surface as to the complexity of black holes, but hopefully that gives you some idea of the forces at play, and I would advise you to stay away from any if you can. That's it for this week. Next time, back down to Earth, where we'll be weighing up whether Wegovy, or semaglutide for its chemical name, the new weight loss drug everyone is talking about, could work for you. Popular with Hollywood actors and TikTok stars, we'll dissect how this drug, designed for people with diabetes, helps you feel less hungry in the first place and fuller for longer after you have eaten. Although, and we'll be mentioning this next week, people do experience side effects, nausea, diarrhea, even heart palpitations, and complain that when they come off the drug, their appetite returns to normal and they find it difficult to keep the weight off. So is this another weight loss fad, or could this pave the way for even more effective appetite-reducing medications? We'll find out. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Will Tingle. Thanks for listening. And until next time, goodbye.